Well, at least our chair is an astronomer. I'm a chemist. So as a chemist, I care about molecules. And as astronomers, you might like to care about molecules occasionally because they can be really interesting probes of the physics that's going on, the chemistry, and maybe even the biology when we get to our next generation of telescopes. And if you've ever looked in molecules in cool stars, exoplanets, you might have come across something. Have we got a? Oh, good. Might have come across something like this, which basically there's an online website called Exomol where you can get high resolution spectral data of a large number of molecules. This list might be out of date. If you're looking for a small molecule and you want to find it in some star, you want to find it in some exoplanet, there might be data and hopefully data for you to enable you to do that. If you're interested in is not, by all means, truly rely on astronomers coming up to us and going, we don't have data for that. Can you help us out? So, yeah. And when I say what data we've got, I'm going to talk to you about the really high resolution stuff. My student is going to talk to you about some medium resolution stuff that goes beyond this sort of, 50 molecules up to something like 2,500. But when you're doing the high resolution stuff, you're looking for something called a line list, which is literally a list of every single energy molecule and the intensity of the transitions between them. And what I mean by this is millions, billions of transitions. And these can be really useful for assessment of fundamental frequencies. So you figure out the proton to electron mass ratio here, then in some part in the early universe. Characterization of exoplanet atmospheres, which I say would be the biggest current application. Atmospheric pollution, so this sort of stuff's useful on Earth. And then if you're looking at isotopologues, it's useful. Now, I've been in the astronomy community for long enough now that I got subject to these exciting memes in about, 2015 odd. But fortunately, recently there was present, and we've got JWST up there. And so that's giving us all sorts of spectra that are really what all the work doing since about 2005 has been trying to do. So for example, this is a hot Jupiter exoplanet. We've got a wavelength, we've got the amount of light absorbed. Carbon dioxide would have been done with Exomol line list. There's actually a little peak on the left there, that's sulfur dioxide, that would have been done with an Exomol line list. And there's also another peak that you can't see here, but we don't know what it is. And my student later is going to tell you about how we're helping figure out what it is. But the astronomers, while they were waiting for JWST, didn't just sit there and do nothing. What they did is realize that ground-based telescopes, you had the huge noise due to the atmosphere, but what advantage you had is really, really high resolution. So with that high resolution, you could use a technique called high resolution cross correlation, which literally, if you've got spectral lines, and then if you've got, well, for this molecule, it should be here, and you could match them up. And so if the observation and the template spectra is what it's called, if they were closely enough matched, then you said, we found this molecule. And that was useful even if you had really quite high signal to noise. And existing data was not good enough. So this is a paper that came out 2015, which was literally, please get some data for TIO. And I've been to conferences where everyone was saying, we really need this TIO data. The reason they need that is you look at this really, really high resolution. The black is the observation of an M giant, where definitely TIO is out. And then the orange and the green and the blue are three modeled, and you can see they're useless. So when the top one is up, the bottom ones are down. And then sometimes they just have peaks in different places for random reasons. And really, they were like, we cannot find titanium oxide because the line list data wasn't good enough. So I think that's a common thread that as chemists, as molecular spectroscopists, for astronomers, and as their astronomers get better and better and better, the data that we produce has to get better and better and better. For a chemist, 0.35 wave number accuracy, we did some studies on this theoretically, it's like hundreds of wave numbers off. So getting that is really, really difficult. And in order to do that, I'm looking at the wrong version of my slides. Never mind. Can I do that maybe? I was wondering where those animations went. There we go. That's all right, we'll get there. So I wanted to show you this slide. So if you've got an observation, so you know the situation they've got there, they're going, we can't find this molecule, what's going on? And what I would say is there's this big list of things that it could be. I'm not going to go through absolutely all of these, but I'm going to go through most of these as we go. And if the answer to any of these questions is yes, it might be the line list. And if the answer is no, then it's probably the astronomy. You're not understanding the chemistry. Something's gone wrong on the astronomy side rather than the molecular data side. So in the case of this data here, it was a transition metal, titanium oxide. It was an electronic, so they're a lot harder for us to model than vibrational transitions. So for chemistry, then when you go into the visible or UV, it was high resolution. And in particular, the line list was developed, the one they were using was developed about in 1998 and didn't use the modern techniques. So what are the modern techniques? Well, you've got the data users, astronomers. You've got the experimental data producers, so they're the spectroscopists in the lab doing lasers. You've got the theoretical data mod producers, so those doing quantum chemistry, simulating the model space. And then you've got a lot of interplay between, and I would consider myself primarily a data modeler. Really, everyone has to talk to each other and make sure that we're all communicating in the same language. And if we do that, then we can figure out what's going on. But if any of those things are missing, then we end up with data that's useless or not addressing what the astronomers are doing, and really it's a big mess. So we need synergy and communication, which is part of the reason I come to astronomy conferences and present. So the experimental data is really, really important if you want high accuracy. So if you're doing that high resolution measurements, you really need experimental data to get you the accuracy. You don't have experiment, sorry, you're not really going to find it. The other thing is if you're not using modern techniques, then even if there's experimental data out there, it might not be being used effectively. So in particular, what's often the case is about from the 1970s to 1990s, there's like 20, 30 papers on your molecule, but no one's brought them all together. And a lot of what we do is bringing them all together and then figuring out what can we say about it. The other thing that happens is you do computational quantum chemistry, and that complements the experiment because it gives you intensities, it gives you isotopologues, and it tells you what happens beyond those 1,000, 10,000 lines that the experimentalists measure to the millions or billions that might contribute to the stellar exoplanet spectra. And these are all the things that contribute to making the quantum chemistry hard. And therefore, when you've got lots and lots of electronic states, you get very large errors and you need to worry about it. Now, modern techniques can get around this. So if you use experiment and computers properly, this is the 2019 when I produce, that green is going up and down with the black. Good, we can use the green to find TI. What was a bit surprising to me was the orange is bad, but this Player's blue data was produced in 2012. So that was before the original paper. That's not bad. I'd like to think the Toto, the one that I produced, is better. Otherwise, why did I produce it? But honestly, they used the wrong line list because they didn't understand the technical subtleties of what they really needed for communication. So communication. This one I'm showing you just because I think it's really pretty. So the top one is the experiment, and the strong lines, you think, okay, they're the signal. And all these little lines, I thought, oh, they're just going to be noise in the experimental spectra. It's not noise. Literally, all those little lines are isotopologues. So instead of being 48 titanium, it's 49, 46. And if you model all those properly, you reproduce the experimental spectra really, really well. And so since that was published 2019, since then we've done a few molecules. My students have started to take over doing this. So Anna's graduated, Anna graduated her PhD, Armando graduated his honours. Thank you. And so we use is that variational line list. I can tell you details later. Quantum chemistry really well. That provides the completeness, and we put in the experimental energy levels. And what we get from something like that is, this is zirconium oxide. The black is everything the molecule absorbs according to. The red is the previous data. So you can see that if you're using the red to try and do that high resolution cross correlation, you're not really going to be very accurate in many regions. And this blue line is what we trust to be accurate frequencies. So if you're using our new data and you're in this spectral window, so about 600 to 800 nanometers, you're good. You can use that high resolution cross correlation. But if you're out there in 400 to 500 nanometers, you see how our trusted to be accurate to high frequencies is much below the actual data, the actual line list. That means that I don't trust that to be accurate to that point sub-wave number accuracy we need for this high resolution cross correlation. And you can do that for molecules. So this is CH, perfect. NH is perfect, but you can see in the visible region in the middle, there's just no absorption. So you're not going to see this molecule, which is also a problem. TIO is pretty good in most things. Do note you need to use the latest. The website, not the 2019. Going in the future in this field. Indicate, make sure data are very strong. The Marvel approach is that experimental data coming in and using different sources of data to come together. And these are a checklist of reasons you might find issues. Come and talk to me if you're concerned.
Thanks, Laura, and thanks for being almost exactly to time. I love it. Yes, Eckhart has a question.
I was wondering if you could comment on the effect of star spots on absorption spectra and how you decorrelate those effects.
So star spots are going to have magnetic fields. So modeling magnetic fields on the effector spectra is, the magnetic fields are going to be hard to do. There's definitely ways to do it, but I'm not an expert in them, but I can find out about that if you'd like. The lower temperature, you just change a number. Instead of modeling it at 5,000 Kelvin, you model it at 4,000 Kelvin. Yeah. So it's definitely doable, and magnetic fields are interesting.
On the data availability thing, the virtual observatory provides a protocol for sharing line lists called the Simple Line Access Protocol, I think it is. So that's a useful way of being able to find and discover them because you can query on lots of parameters and that kind of thing. So
I would say there, I actually rely on my postdocs, the community around me. So I produce data, and then there's a community that links it over. I'm not precisely sure of that one, but what I would suggest is it's probably atomic. Molecular data is so much bigger. The problem is when these get to gigabytes, then it mucks up all the thing. Well, actually, then I should get someone to write it down. I'll come and talk to you after. That would be cool.
Do we have any questions online? And maybe our next speaker, Brendan, if you're in here, come down. What's your favorite molecule?
Not TIO. I don't know. I like diatomics because all their complexity is in one dimension. So that's good. I've just spent a bit too much time on TIO. Otherwise, it'd be a good one.
It's time to move on from that. Excellent. Let's thank Laura again.